Hello, hello, hello. In this worked example, which is entitled N2 in Action, Newton's second law in action, we're going to take a first simple example of how Newton's law can be applied when you apply a force to a moving object. We'll take a specific example. You might imagine that the situation uh, applies to a curling stone sliding on a block of ice. So we have a mass, let's say our curling stone has a mass of 2 kilograms, and the XY plane is the plane of the ice. And at some initial time, relative to some origin, let's say that the position of the curling stone is given by this vector quantity, the position uh, 1.5 meters x coordinate, 6.0 meters y coordinate, and it's in the z equals 0 plane, and is moving with this particular velocity. And in the first part of the problem, we just want to calculate where is the curling stone going to be 3 seconds later. Well, that's easy, of course. So to help keep track of what's going on, I've set up this little XY coordinate system here. And at time 0, the object is located at a position, an X coordinate of 1.5 and a Y coordinate of 6. So we'll put a little dot at this point here, and that little dot represents the position of the object at time 0. And it's headed with an initial velocity. If you look at the numbers here, the initial velocity is pointing sort of down and to the right, so pointing sort of in this direction, somewhere like that. So we expect a little while later the object is going to be somewhere down and to the right, but let's find out exactly where. So in general, for an object moving with constant velocity, we can represent the final position uh, is equal to the initial position. So the final position we'll call r sub f. The initial position is r sub I. And then if the velocity it's moving at is v times delta t. This is what we can call the position update formula for an object traveling at constant velocity. This is how we calculate the new position uh, given the old position. V times delta t is, of course, the change in position. So in this problem here, r sub I, we'll use our vector notation. R sub I, the initial position at time 0, it has a value of 1.5 comma 6.0 comma 0, and the units are meters, and then plus the velocity, which is 2.0 comma minus 2.5 comma 0 meters per second times delta t, and delta t is of course 3 seconds here. That's the time between time 0 and time 3 seconds. So this is just equal to 1.5 comma 6.0 comma 0 meters plus, and it's going to be 3 seconds times 2 meters times 2 meters per second is 6 meters minus 7.5 comma 0 meters. And then the rules for adding vector quantities like this are just the individual components add. So we're left with the final position at 1.5 plus 6 is 7.5. 6 plus negative 7.5 is minus 1.5, and 0 plus 0 is 0. So this is the final position, the position at a time of 3 seconds. So an x coordinate of 7.5 units and a y coordinate of minus 1.5. So that puts the position at time of 3 seconds, r of 3 seconds is somewhere like here. And we can even mark on our graph here the velocity, this initial velocity vector, or the velocity throughout the motion, v, is clearly in a direction that connects the initial position with the final position in this case. So the trajectory of the object during the first 3 seconds is this yellow line here. And then during this window of time between t equals 3 seconds and t equals 5 seconds, something happens. Instead of the curling stone sliding with zero acceleration, there's a force, a constant force that's added. So maybe a wind starts blowing to create this force, and that is clearly going to, according to the second law, going to cause the stone to accelerate, and it's easy to calculate what that acceleration is. So during this window of time, the acceleration of the stone is no longer zero. It's equal to the net force that acts on the stone divided by its mass. And we're given in this case, the net force is given to be minus 4.0 comma minus 2.0 comma 0 newtons divided by a mass. We said previously that the mass of the stone was 2 kilograms. So the acceleration of the stone during this window of time is going to be minus 2.0 comma minus 1.0 comma 0, and the units, the SI units for acceleration are meters per second squared. And once we know the acceleration, it's easy to answer the question that's being asked here, which is what is the object's change in velocity during this window of time? Well, delta V for an object undergoing constant acceleration A, delta V, the change in velocity, is just that acceleration times the duration of the time interval. So this is just minus 2.0 comma minus 1.0 comma 0 meters per second squared, and delta t is the duration of the window of time between t equals 3 and t equals 5 seconds. So that's just 2 seconds. And so we get the change in velocity is minus 4.0 comma minus 2.0 comma 0, and the units are of course meters per second. Okay, so we have two questions on the table here. One is just to follow up on what the calculation we did on the previous screen. Let's actually write down what we calculated the change in velocity during the window between 3 and 5 seconds. Let's write down what the velocity is at t equals 5 seconds, and also what the object's position is at t equals 5 seconds, and then we'll be able to begin at least to sketch in what the trajectory looked at during the time interval between 3 and 5 seconds. So the velocity at 5 seconds is going to be equal to the velocity that it had at 3 seconds plus the change in velocity that we just calculated. So plugging in numerical values here, we get, so this was the velocity during the first 3 seconds of the motion. The change in velocity that we just calculated is this quantity here, and then just adding these numbers together, 2 minus 4 gives minus 2.0, and then minus 2.5 minus 2 gives minus 4.5, and 0 plus 0 is 0 meters per second. So at the end of 5 seconds, due to the acceleration that the object experienced, the velocity is now no longer pointing down and to the right. It's got a negative x and y component. So the velocity at 5 seconds is pointing somewhere down here, like that. Now, the next part of the question is, where is the object at t equals 5 seconds? What is its position vector? So how are we going to calculate that? Well, the general rule for calculating position when you have constant acceleration is that the final position is equal to the initial position. And now there are going to be two terms here. There's going to be an initial velocity vector times the duration of the time interval, delta t, and then the next term is going to be a 1/2. Now the acceleration is constant, we're calling that a, and now there's a delta t squared term here. So let's plug in numerical values. We want to know where the object, the stone, ends up at the end of our time interval. Its position at the beginning of this time window in which it was undergoing constant acceleration is given by this quantity here. So Ri is 7.5 comma minus 1.5 comma 0 meters. And now the velocity at the beginning of this window is this quantity here. So we're going to plug that in, and this is 2.0 comma minus 2.5 comma 0 meters per second times the duration of our time window. It's a 2-second duration time window. So that's this term here that we just typed in. And now we've got one more term to add in. So we have a plus 1/2. The acceleration, we've said, is, you'll have to look back at the previous screen, but you'll have to trust me or trust me that the answer that we found for the acceleration is minus 2.0 comma minus 1.0 comma 0, and the units are meters per second squared. Now, times the duration of the time interval squared. So this is times 2 seconds quantity squared. And if you plug in if you just do the math here, I'm not going to take the time to do it. You should work this out on your own. But what you find is that the position vector at t equals 5 seconds is got these numerical values. So an x value of 7.5, a y value of minus 8.5. So on our little graph here, 7.5 to in the x value minus 8.5 puts us somewhere right around here. And we've already argued that the velocity at this point is pointing, if you look at this velocity vector, it's got a velocity vector heading down and to the left, sort of down in this direction. So what that must mean is that the trajectory between t equals 3 seconds and t equals 5 seconds is got to be doing something like this. It's got to be curling around so that by the time it gets to 5 seconds, it's heading in the direction indicated by this velocity vector here. Oops. This velocity vector here, so down and to the left. So in this last part, we assume that after t equals 5 seconds, the force is turned off and the object moves under the influence of no forces. So let's try to sketch out the whole trajectory, say for a time period between t equals 0 and t equals 8 seconds. So 3 seconds, so that includes the time 3 seconds after the force is turned off. So you're going to end up after 5 seconds. It's going to, as we said, it's going to continue to move at whatever velocity it had at 5 seconds because there's no acceleration anymore. So it's going to move in a straight line. So this little sketch here, where I've sort of played connect the dots, indicates the big picture of how we expect the object to move during this entire 8-second window. And let's try to verify that by doing a numerical simulation. There I wrote a little VPython program to simulate what's going on in the problem using our Euler's method. And the basic idea is we create a ball that is going to leave a trail behind. We set up the initial position and velocity of the ball according to the numbers given in the problem. And then here's our main loop where we're going to run the Euler's method. But the twist is that to comport with what's going on in the problem, the acceleration that the ball undergoes is going to depend on where we are in this 8-second window. So if you're between the window of 3 and 5 seconds, the acceleration ends up being non-zero and equal to this number here. And we'll have the ball indicate this value of the acceleration by leaving a red trail behind. And otherwise, both before t equals 3 seconds and after t equals 5 seconds, the acceleration is 0, and we'll indicate this by having the ball leave a yellow trail behind. And then at the end of the day, when we exit the loop, we're going to just print out the final position of the ball and the final velocity of the ball. So let's see how it works. We hit run, like so, and the ball is off. It's leaving a yellow trail, not zero acceleration. Now the acceleration is non-zero, back to zero acceleration. And if I change the scale here, we can see maybe the final position of the ball is given at the bottom of the screen here, and the final velocity. So that lines up pretty well with the expectations that we had based on the sketch that we made. For this episode of, I guess this is a worked example. Hope to see you again soon. Bye-bye.